I'm Akiko Kishida at NIED. The title is Shake Table Test of a Partial Model of a Roller-Supported Steel Roof. Part 1. Preliminary Test with Steel Clamp. Steel roofs supported by RC substructures and roller bearings are widely used for school gymnasiums in Japan. Damages around roller bearings have been often reported in large-scale earthquakes. It is considered that out-of-plane responses of RC substructures causes these earthquake damages. Many school gymnasiums in Japan are expected to be used as evacuation shelters when natural disasters occur. It is necessary that they are fit for use after earthquake. These are the objectives of this study. For this purpose, we conduct shake table tests of a 1 by 2.5 scaled partial gymnasium model, which consists of a system truss roof, cantilevered substructure, and roller bearing. In Part 1, we focus mainly on energy absorption and response control performance of friction damper and conduct a preliminary shake table test of a partial gymnasium model with steel substructure. We extract a part of the gymnasium, which had earthquake damages in 2016 Kumamoto earthquake. The RC wall upper than the third floor, roof truss, and roller bearing are extracted. The similarity rule is listed in Table 1. Although the original substructure is made from reinforced concrete, in the preliminary test, it is replaced to a steel clamp. The overview of roller bearing is shown in Figure 2. Before the shake table test, we conduct a static loading test of the roller bearing with friction damper to examine the friction coefficient. The experiment setup is shown here. Cyclic horizontal displacement is given to the slide table, and horizontal force and damper bolt tension are measured. The list of loading patterns is presented in Table 2. These are load displacement diagrams. When horizontal load is close to zero, slip is seen. It might be caused by gaps between bolts and plates. After displacement of 7 to 8 mm, horizontal load becomes almost constant. Horizontal load depends on loading speed, and higher loading speed makes load higher. The friction coefficient of each test patterns are plotted here. It can be estimated to be 0.85 on average. We conducted the shake table test using the large-scale earthquake simulator owned by NIED. The input waves are a sine wave and an artificial seismic wave. The frequency of sine wave is 8 Hz. This is the list of dynamic test cases. I show the video of test case D4. These are test results. This is the transfer function. The natural frequency was 9.16 Hz. These are the horizontal load displacement relationships of roller bearing. As shown in figures of sine wave input, the horizontal rows were almost constant. In the case of 75% seismic wave input, almost no relative displacement between base and slide plates were seen. When input level increased, relative displacements were observed. The friction force without damper is estimated to be about 12 kN. The friction coefficient is 0.15. Friction force only from the damper is estimated to be 8 kN. The friction coefficient of damper is 0.8. This corresponds to the coefficient obtained from the static test. The conclusion is this. Thank you for your kind attention.